Okay, let's start. Good evening, everyone. So, today is the 10th week of Fundamentals of Power Electronics tutorial session. Today, we shall discuss uh, some DC-DC converters. So, we have already discussed the non-isolated DC-DC converters like buck converter, boost converter, and buck boost converter. And we have also discussed some isolated converters like the forward converter and the flyback converter. Today we shall discuss some more isolated converters, which are push-pull converter, half-bridge converter, and full-bridge converter. We shall see their operating principle and the various waveforms. And afterwards, we shall solve the numerical problems regarding these converters. Okay. So basically, push-pull converter, you can have the circuit of the push-pull converter after doing certain variations in the forward converter structure. So in the forward converter, there was a DC source in the input, and then you had one transformer winding, and in the secondary side you had another winding. But here, if you see, the difference is that in the secondary side now, it is a center tap winding. So there are two windings, and from the center, we have this tap, and we have two diodes. So this is one diode, and this is another diode. So this is called center tap configuration. And in the primary, actually, we have again two windings. So in the forward converter, we saw that we were connecting another winding for resetting the flux. So here we have in the primary we have two windings, and all these windings are coupled by a single core. So there is this winding, and the dot polarities are as shown here. So the dot polarities are like this, and here instead of a single switch we have two controlled switch. We have two control devices. One is Q1, another is Q2, right? So this is the circuit of a push-pull converter. Now we have to see how does this work. So first of all, so Vi is this. This is the input voltage, right? So suppose we have taken some instances. If you see in the right hand side here, the waveforms are shown. So we shall discuss one by one. But firstly, we have divided the total time period in certain intervals. Let's see the first interval where Q1 is on. This semiconductor device is on. This transistor is on. When Q1 is on, then current can flow in this path from Vi. So the dot polarity will be something like this, here positive and here negative, right? Because the positive terminal of the DC bus, DC supply is connected here. So this is positive, this is negative. So current can flow like this in this path. And in this interval, Q2 is off. So Q2 is off, so this is open, and there is no current in this winding. But as these windings are coupled, so if Vi voltage is getting induced here, then Vi the same voltage will be induced here if these are 1:1 windings, and here also you will get some induced voltage based on the turns ratio, right? So you will get some voltage based on the turns ratio. So suppose for the first interval when Q1 is on, so this is suppose positive, this is negative, and this induced voltage is Vi. So then in this winding, if this winding is 1:1, So here also the same voltage will get induced. So again you will get Vi here. And for the center tap winding, suppose this is N1 in the primary, and here suppose this is N2. So they are, both of them are N2 and N2. So based on this turns ratio, you will get some voltage Vi multiplied by N2 by N1. So here the induced voltage will be Vi times N2 by N1. Okay. That will be the induced voltage in the center tap winding. In each winding I am talking about, because there are two windings here. So like this, the voltage will get induced. Now you can understand, when Q1 is on and current is flowing like this in this loop, then obviously if there is some positive voltage here, this diode will get forward biased, obviously D1. So current can flow like this, through this inductor and through this load back to the winding. Right. So this will be the current path. This is the current path. As soon as this diode gets forward biased, this diode can't conduct. It gets reverse biased. So now no current will flow through from here. Only the current will flow like this in this interval when Q1 is on. Next, we will see an interval where both these devices are off. Q1 is also off and Q2 is also off. So when both these devices are off, then what will happen? Then if you see the secondary side, now this inductor, when Q1 was on, the inductor got energized. Now the inductor will freewheel. Inductor current will freewheel. What is the path? So the current will come like this. It will come like this, and here it will split into two parts. Through this winding like this, and through this winding via this diode, and then again back to the inductor, right? So this will be the current path. Now here if you see, this current is coming towards the dot, and here the current is coming out. So here the mmf in this winding and this mmf in this winding, they will cancel each other. Okay, and there will be so here there will be no voltage induced during this interval when the inductor is freewheeling. As there is no voltage here, then uh, therefore there will be no voltage in the primary winding also. So the 0 and 0, there will be no voltage. So that's why this pole voltage P, this is 0 here. First this is NVI, where N is N2 by N1, then it is 0. In the next interval, we will see that Q2 is on and Q1 is off. The opposite. First Q1 was on, then both were off. Now Q2 is on and this is off. So again the current path will be now through this winding like this in the upper winding. And this is off, so there is no current in this winding. So again there will be Vi voltage here, and here we will get NVI voltage. And again now what will happen? Now this diode will conduct, because now the polarity, now the current is flowing like this. So the polarity is positive here, negative here. Similarly, positive here, negative here. So now this diode is forward biased and the current will flow like this. Okay, from here to this diode through this inductor, and then again back to the winding. Okay, so this is how this voltage fluctuates. NVI, then 0, then again NVI, then 0, like this. After that we have the waveform. Here is the inductor current. So here you are giving some positive voltage here. So, and here this voltage is greater than V naught. So the current will rise. And when the inductor is freewheeling, the voltage across the inductor is minus V naught. So the current falls. Current slope is negative. This is the inductor current. Then the waveform that we have shown is the flux waveform. The flux through the core. Okay. So we know that. Huh. Well,
So and vi minus v.
you were not audible. Can you just text the question in the message section? You just type and send it. Akshit, can you please type your question? Because you were not audible. Yeah, so I was discussing the flux waveform. Uh, Here, basically, when there is some positive voltage across these windings, then the flux also rises like this. Okay, and then there is zero voltage, so the flux remains at its position. It remains at the same value, and then again it drops like this. Okay, so the average value of the flux is zero here. Afterwards, we have the current waveforms, the current through D1 and the current through D2. So when Q1 is on, the entire load current is flowing through this diode D1 because this is forward biased and this is reverse biased. So the entire load current flows through D1. So this current is exactly equal to the inductor current here. But when both these switches are off, then the current gets split, right? The current has now two paths. So the current gets divided equally between D1 and D2. That's why now this current is half of this. The current is like this. And then when Q2 is on, then this diode is forward biased and this is reverse biased. So the current through D1 is zero. Current through D2 is exactly same as D1, just that it is shifted. So D1 carries the whole current when Q1 is on, and D2 carries the whole load current when Q2 is on. But their waveforms are similar, same actually. Okay. Uh, Sorry, I think I disconnected. Uh, am I audible?
Yes, ma'am.
Yeah, so I was discussing that the voltage across device. See, you have approach to draw the voltage across Q2. It will be same, just that it will be phase shifted. So when Q1 is on, then the voltage across it is 0, and when both of them are off, then each switch will have to block a voltage of equal to the input voltage in this period. And then when Q2 is on and Q1 is off, then the voltage across Q1 is twice the input voltage, because there is this supply voltage and then there is this voltage across this winding. So if you apply KVL in this loop, you will see the voltage across Q1 is 2 VI. Okay. So the disadvantage of push-pull converter is that each device has to block twice the input voltage. Okay. So this is one disadvantage. And here the output voltage and input voltage relation is 2N VID. Okay. Where N is the turns ratio, VI is the input voltage, and D is the duty ratio of the switch. Why this 2 comes? Because if you observe this waveform, so you see the frequency of this waveform is twice the time period. So our whole time period is from here to here, right? So Q1 on, then again 0, then Q2 on, then 0. So this is the whole time period. So this pole voltage is basically as the frequency which is twice the switching frequency. So that's why this 2 factor comes. The relationship is 2 in VID. And similarly, you see the inductor current frequency is also twice the switching frequency. This is our switching time period, starting from this to this to this. But during this interval, the inductor current has completed 2 complete cycles. So that's why this 2 comes in the expression. One problem comes. There is an issue in the push-pull converter which is called the flux working. What is flux working? So flux working is that when ideally actually we assume that there is no voltage drop across the devices when they are on, but practically that is not the case. With some small voltage drop we see set across the transistors, and it may so happen that the voltage drop across Q1 and Q2, they are not exactly same. Even though you select the same device for this Q1 and Q2, but still there may be small miss in the device. Okay, that not equal to VC set 2. What may happen is there will be some flux accumulation. Actually, the average, ideally, the average value of flux should be 0, but this does not happen. Why? Because the volt second balance is not maintained. So during this time, if you see the voltage, then the total primary voltage when suppose Q1 is on is what? 2 VI. Because this is on, so VI here, and again some voltage VI is induced here because they are coupled by a core. So the total voltage is VI. Okay. And here it is minus 2 VI when Q2 is on. Right. But actually, what is the voltage? If you consider the drop across the device, then it will be twice Vi minus Vc is at 1 when Q1 is on. And during this time, it will be Vi minus Vc is at 2 when this switch is on. So if this parameter and this parameter, they are not same, then the area under this in the positive half and the area here, they are not same. That's why the volt second balance is not balanced. The volt second balance uh, is not getting maintained here, right? If volt second balance is not maintained, then there will be maybe some very small voltage, average voltage actually, in the positive half or in the negative half. And if you see the flux, so the induced voltage is N d phi by dt. So if there is very some small average voltage, then phi will be what? Integral of dt. So as time goes on, so there will be a steady rise in the flux. Even though this voltage may be very small, but still there will be rise in the flux. And as time goes, the flux will accumulate more and more. And it may lead to saturation of the core. And if the core is saturated, then the converter will not work. Okay. So that's why this is a problem. This is called the flux working issue. Now we will have to see how we can get rid of this problem. Yeah, so here it is shown. So suppose initially the average value of flux was 0, and this was the swing in B, the flux density. Okay. And this is the primary voltage. Now, as time goes by, now there is some, as time is, now phi is integral dt. So as time increases, phi also increases. So now the phi has some value like this. So suppose now the average of B is here and the swing is like this. So you see now the average of flux is no longer 0. It has some definite value. And here again the flux has significant average value. So now like this, and it goes towards the saturation, right? And as it goes towards the saturation, now the slope of phi has been reduced. So there will be some drop in the induced voltage, right? Because now the slope has reduced here. It is in the saturation region. So it may cause problem. The converter will not work, okay, if the core is saturated. So what is done to get rid of this problem? So what we do is basically some two additional windings are connected here like this on the same core. These are two additional windings, but their power ratings are very small. They have to carry very small current, only the magnetizing current. And here diodes are connected like this. Okay. So these two additional windings are connected just to get uh, the volt second of this due to this switch and this switch. So when Q1 is on, so this diode is forward biased and it will it will conduct, and when Q2 is on, then this diode will conduct. Okay. So here we will get the voltages corresponding to when Q1 is on and when Q2 is on. And here we can find out the error. We can find out the difference between the positive voltage and the negative voltage. Ideally, it should be zero, but if there is some mismatch between the positive voltage and negative voltage, then this error is fed to a PI controller, and some correction voltage is generated at the output of the controller, which is added with the pulses, the PWM, the pulse width modulation circuit of the converter. Okay, so here this is the PWM circuit. So this is the reference, this is the feedback. So this will be discussed later in detail. But here the control voltage is compared with a triangular voltage or a sawtooth voltage, and then after this comparison, some we get the pulses that is required to drive these switches. Okay, with these pulses we add these correction voltages so that the duty ratio of Q1 and Q2 can be controlled, so that the volt second is maintained and there is no saturation. This is one method. Another method is there that we will discuss for this half bridge converter. So this is the half bridge converter. This is another DC-DC converter. Okay. Here, here this is the AC grid, and this we already discussed. There is a diode full bridge rectifier. Then after this diode rectifier, the DC link is split in two equal parts by connecting these two capacitors of same value. So the DC link is split in two halves, and there are this is called a half bridge. This configuration is called a half bridge. So and from this switching nodes, this transformer is connected. In the secondary side, it is center tapped. This portion is similar to push pull converter, and here we get the output voltage. Right. So here the load is connected. How does this work? So this is VDC by 2. When Q1 is on, then current can flow in this manner, in this loop. And when Q2 is on, current can flow in the opposite direction through the transformer like this, through Q2. Right. And when Q1 is on, so VDC by 2 is induced here. This diode will conduct, and this diode is reverse biased. Same way, when Q2 is on, then minus VDC by 2 is here. So now this diode will conduct and this diode is off. Okay. Here the output voltage is in VDC-D. So here also this two factor will come because this is a center tapped configuration. But as the DC link is VDC by 2 here for each interval, that's why this 2 VDC by 2 and here 2, these two are cancelled. So it is in VDC times D, where D is the duty ratio. Okay. This is the half bridge converter. Now the problem of flux walking also happens here because it is possible that the VC set of Q1 and Q2, they are different. The voltage drop across Q1 and the voltage drop across Q2 is different. So what we can do is, another solution is we can add a capacitor in series with the transformer. What is the advantage? Then the capacitor can block the DC portion of the voltage and only the AC portions will come here. That's why there will be no imbalance in the volt second. Because now the capacitor, the DC portion of the voltage will appear across this capacitor. And while choosing the capacitor, we will have to uh, take care that the current rating of the capacitor is uh, is uh, is proper, so that it can carry the current that is flowing through the transformer, because it is in series. So the current that is flowing through the transformer, the equal current will flow through this capacitor also. So the current rating of the capacitor is crucial. Okay. So yeah, this was half bridge converter. And there is another converter which is full bridge converter. So this is this unit. This is called one half bridge, and two half bridges are there. So this is a full bridge. There are two half bridges. This is one, and this is two. So this is called a full bridge converter. Otherwise, all these things are same. Here there will be the supply voltage VDC. Here this is the center tapped transformer. Uh, and when Q1 and Q4 are these two diagonal devices are on, then current will flow like this through this switch. So if you just draw the supply here, so uh, the current can flow like this. And when and there may be, and similarly when Q2 and Q3 are on, current will flow like this through these diagonal switches. And there may be an interval where both all these four switches are off. Then the inductor current will free will here, so there will be no voltage across the windings in that case, when the inductor current will free will through these diodes. Okay, so this is the full bridge converter. Now we shall start the problems numericals. Before that, if you have any question, you can ask. If you don't have any question, let's take a break of 5 minutes, and we may come back. We shall come back after uh, at what is the time? Now it is 6:37. So we may come back at 6:42. You may The first problem says that a push-pull converter shown in the figures is supplying a 20 ampere constant load current at 12 volt. So the load current value and the load voltage value are given. The turns ratio of the transformer is N is by NP, which is 0.5. N is by NP is 0.5. The on-state voltage drops of diodes and transistors are given 0.volt and 1 volt respectively. The due to the primary transistors is 0.25. What the average input current here? Loss and input can consider the load current is constant current. The input current, the ripple in the input current is also negligible. Full converter, and these are right. And what they have asked the average input current. So this I in, average value of I in, they have asked. So what we can first apply KVL. Okay. So the secondary voltage, what will be the secondary voltage? The second one plus V in. Suppose when uh, when you on, then current flows like this. In that case, one is forward biased, so current flows like this in the secondary circuit. And if we apply KVL here, V VD1, the drop across this diode, then V out. Okay. So here we have calculated what is VS 12.54. The turns ratio is given 0.5. This is a center tap transformer. So NPTENS, the turn in one of these windings. So P and NS is 0.5. Uh, here, so the primary voltage will be NP by NS, which is 2. Here, here in the question, NS by NP is given 0.5. So suppose if this the number of turns in the primary is suppose 20, then it will be 10. Okay, so the primary voltage is twice the secondary voltage, which is 25 volt. Again, if you apply KVL in the primary loop, suppose in this loop, then you will get the input voltage is the summation of this primary voltage and the drop across this device. That's why it is written V Vp plus Vq. So V input voltage is 26 volt. Now we have got the value of the input voltage, right? What is the average current through each transistor? The average current through each transistor is IQ is I in by 2, half the input average current. Why? Because when Q1 is on, then the input current is carried by Q1. And when Q2 is on, the input current is carried by Q2. And in these intervals, when both these switches are off, there is no input current that gets drawn from the input, right? So that's why average value of each transistor would be half the average of the input current. That's why IQ is IN by 2. The average current through each diode is I naught by 2, where I naught is the load current. Because we can neglect these ripples in, because in the question they have asked to assume ripple, they have asked to neglect the ripple. So if you just assume the square wave type waveforms, so in this interval, when Q1 is on, the D1 diode carries the total load current. After that, when the inductor is free, current is freewheeling, then the load current is split and each diode carries half the load current. And then when Q2 is on, the diode D2 carries the total load current. So current through D1 is zero. This is the current through D1. Similarly, we can say for D2 also. So if you find out the average of this current through, you can choose either ID1 or ID2. The waveform will be same. So here it is I naught and the
Screen is not,
duty ratio is given. So, yes,
the screen is not visible.
screen is not visible. Okay, I shall share. Now is it visible?
No, ma'am.
Now is it visible?
No.
It is not visible.
Yes, ma'am, it is visible.
Okay, okay. So till which point you could see?
Until IN equal to 10 ampere.
No, I am saying that in between the screen was not visible. So last when you saw the screen, when could you see the screen?
Ma'am, when you start introduce the problem.
So did you see this problem when I started?
No, ma'am.
Okay, so till this point, could you see full bridge converter?
Yes, ma'am.
Okay, so I shall start this numerical again. Here, so the push-pull converter is given here, and some data is provided. So the converter is 20 ampere. Just a second. The screen is visible, right?
Yes, ma'am.
Yeah. So what they are asking is that the load current value and the load voltage value is given, and the turns ratio is also given, NS by NP. The turns ratio is given. The on-state voltage drops of diode and transistors are 0.5 volt and 1 volt. The duty ratio of the primary side transistors is 0.25. So the duty ratio is 0.25 for both transistors. What is the input current? And they have also said that you can ignore the transformer. The transformer has zero losses and leakage and negligible ripple in the load current. So you can assume a constant load current and also constant input current. So first, how we will proceed is first we shall have to find out the input voltage, right? After we find the input voltage, and as we have output current and output voltage value, we can apply the power equation. The input power will be the loss plus the output power. From there, we can find out the average value of I in the input current. So if you, I shall just show, I shall bring the waveforms here so that it will be easier for you to understand. Yeah. So if you see the waveform here, when Q1 is on, when Q1 this device is on, current flows like this, and this is the current. So we can apply KVL here, which is the secondary voltage is VT1. So the secondary voltage is VT1 plus V out. So this is the V out output voltage, and we will also have to add the drop across D1 because they have provided us the data, the forward drop of the diode. So this is the secondary voltage. And we also have the turns ratio here. So we can find out the primary voltage, which is NP by NS times V secondary. So this is 25 volt. Now, if you apply KVL in the primary loop, so if you apply KVL in the primary loop here, then you will see that uh, the input voltage is the drop across Q1. So this is Vp plus VQ1. So okay. Now I have got the input voltage value. Apply and we have to average current through the transistor one and the average current through the diode because they have given the drops across the diode and the transistor, so they are no longer ideal. There will be some loss across the in the diode and in the device. So we will have to find out the current through the device and also the current through the diode. What is the average current through each transistor? The average current through each transistor is half of the input current, right? Because once Q is on the current, and then for some time both of them are off. Then when Q2 is on, Q2 carries the input current. So the average of current through each transistor is half the input current. and the average current through each diode is half the load current. Now that we have the average of transistor and the diode, we can have the power balance equation. Input power is 2 VQIQ because there are two transistors in the primary, 2 VDID because there are two diodes, plus the output power. So VQ is given as 1 volt, the drop across the transistor, and VD is given as 0.5 volt. If you substitute those values, you will get this equation. From here, you can find out IN equal to 10 ampere. So the input current, input average current is 10 ampere. Okay, so let's see the next question. What they are asking, referring to question 1, what is the percentage efficiency of the converter? So this is very straightforward because we have already found out what is the input average current, and we already know the input voltage. We can easily find out what is the input power, which is nothing but V in times I in. And output power we also know because the load current value and the load voltage value is given. So from there, we can find out the efficiency. So input power is this, output power is this. Efficiency is the ratio of, this is output power by input power. So this is output power by input power. So the efficiency is 92.3% here. So let's see the next question. Refer to figure Q1, figure of Q1. What will be the peak inverse voltage rating of the diode if the input to the converter is supplied through a full bridge diode rectifier capacitor filter connected to 230 volt 50 hertz supply with 10% tolerance? So they have asked for the peak inverse voltage rating of these two diodes D1 and D2. And what else is given? So this input voltage is coming from a 230 volt single phase supply. After that AC supply, there is a diode bridge rectifier, and after that there is a capacitor as filter. And the grid voltage has 10% tolerance, and NS by NP is given as 0.25 here. So first of all, we need to find out what is the peak voltage. We have, while studying the diode bridge rectifier, we have seen that the peak value of the output voltage with a capacitive filter, the peak value is √2 times sorry, can you please mute yourself? Yeah, so the maximum maximum value of the input voltage to this push-pull converter is root 2 times 230 times 1.1. Why? Because the tolerance is given 10%. So the peak value is 357.8 volt. And for push-pull converter, the secondary voltage is so the secondary voltage coming across each of these windings, it is 0.25 times Vp max. Vp max is the maximum value across the primary winding. So this is the same as this. So this is 89 volt, and the each diode has to tolerate a reverse voltage of twice the this voltage, secondary voltage. So the peak inverse voltage of each diode will be twice of this secondary voltage, which is 178.9 volt. So the next question is, which of the following statements is false regarding the flux walking phenomena? The first option is, it can cause saturation of the converter transformer. The second option is, flux walking occurs because of volt-second unbalance across the winding. The third option is, flux walking problem can be solved by connecting a series inductance with the primary winding. And the fourth option is, correcting the duty cycle in each PWM cycle can resolve the flux walking problem. So we know that the flux walking problem causes saturation of converter transformer. So this is true. Flux walking occurs because of volt-second unbalance across the winding. This is also true. Third option is, flux walking problem can be solved by connecting a series inductance with the primary winding. This is false. Why? Because we have to connect a capacitor in series. Connecting a inductance in series will not solve the flux walking problem. So this is false. The last option is, correcting the duty cycle in each PWM cycle can resolve the flux walking problem. This is also true that we saw. So the false option is option C. Option C is not true. Let's see the next problem. The next problem says that the power electronic switches in a push-pull converter are switched at 50 kHz with a duty cycle of 0.25. It is supplied with constant current. The the center type transformer is 2.0. The DC input voltage of the converter is provided from a 12-volt battery. What is the magnitude of the output voltage? So here the turns ratio is given, the duty cycle is given, and the input voltage is also given. What is the magnitude of the output voltage? So for push-pull converter, we saw that the output voltage and input voltage relation is 2N V in D, where N is the turns ratio, this is the input voltage, D is the duty cycle. So everything is given here. So this is straightforward. 2 times 2.5, 12 and 0.25. Here that this N is the turns ratio, and this Ns by Np, where Ns is the number of turns of the center tap transformer. Ns is the number of turns of each winding of the center tap transformer. So here this is the total ratio 5, but actually it is 2.5, then 0, then 2.5. So basically this in this portion, this is 2.5, then 0, then 2.5. So Ns by Np is basically 2.5, not 5. 5 is for the whole winding, for this whole winding. But for each winding, it is 2.5. What is the next question? The next question is the half bridge converter circuit is shown below. The output voltage of the circuit is 7.2 volt. What is the duty ratio of the circuit? The circuit operates under continuous conduction mode and assume all electronic switches as ideal. So the output voltage is given. Uh, what they have asked what is the duty ratio of the circuit. Input voltage is also given here, 48 volt. So for a half bridge converter, the input output voltage relationship is this NVDC-D. So N here is N2 by N1, which is 0.5. Right. So this is a 1:1. So this whole winding is 1:1. But as this is center tap, so for the upper half and lower half, it will be 0.5 and 0.5. So N is 0.5 and D will be V0 by 2 and V in, sorry, this is VDC and this is N. So N is 0.5, VDC is 48. So this comes out to be 0.3. This is the duty ratio. So the next problem is the average current flowing through the magnetizing inductor of the transformer in the given circuit under steady state condition. So they are asking what is the average current flowing through the magnetizing inductor of the transformer under steady state condition. Okay, so we have seen the waveforms of a push-pull converter. Right, this is the steady state waveforms of a push-pull converter. So we have seen this is the flux has this kind of a waveform. So the magnetizing current waveform is something like this. When there is this voltage, positive voltage, then the current rises. Then when there is zero voltage, the current stays at its value and then again it falls. So the average current in steady state is zero. The average current is zero. Okay. What is the next problem? The next problem is find out the peak inverse voltage experienced by diode D3 in the circuit shown in question number 6. So the same circuit is here. They have asked the peak inverse voltage of diode D3. Okay. So again we can find out. So here this is a center tapped configuration. So the diode has to has to withstand a voltage that is twice the secondary voltage in reverse biased condition. Okay. So D3 and D4, both of these diodes, what the blocking voltage, the peak inverse voltage will be 2 times the secondary voltage in VDC by 2. Okay. So 24 volt is the correct answer. 24 volt is the correct answer. Because in center tapped configuration, each diode has to withstand twice the secondary voltage. Where we are referring the secondary voltage as the voltage induced across this winding, either across the upper half winding or the lower half winding. That is the secondary voltage. Okay. So what is the next problem? Average DC-DC convert preceding voltage of VDC equal to 48 volt. So this input voltage is 48 volt as shown in the figure. The ratio of transformer winding, the turns ratio is NS by NP is 6. The converter operates at a switching frequency of 50 kilohertz with a duty ratio of 0.5. The peak inverse voltage of the secondary side diodes D1 and D2 is. So this is a full bridge converter. This is one half bridge, this is another half bridge. The duty ratio is given. They have asked the peak inverse voltage across the diodes D1 and D2. Okay. So for any of them actually. Here, again, this is a center tap configuration. So first we will have to find out what is the secondary voltage. Secondary voltage is what? Turns ratio N2 by N1 by times VDC. Okay. 288 volt. And each diode has to withstand twice this value. So 576 volt. As this is a center tap configuration, right? So for a full bridge converter, if we discuss, so first when suppose S1 and S4, these two switches are on, right? Then the current will flow like this. So the polarity will be like this, VDC, right? So here also the polarity will be like this. The polarity will be something like this. And when these two switches are off and these two switches are on, S3 and S2 are on, then the current path is like this through this switch here, like this, like this. So then the polarity will be reversed. This will be positive, this will be negative. And here also the polarity will get reversed. Okay. So you can take any interval, but whenever this diode is reverse biased, it will have to withstand. You can apply KVL in this loop. So if you apply KVL in this loop, you will see the diode has to withstand a voltage that is twice the voltage across any of this winding, either this winding or this winding. That like the voltage will be same. Here also it will be NS by NP times VTC. NS by NP times VTC. And in the bottom winding also it will be same. Okay, it will be same. So the peak inverse voltage will be 2 Vx, which is 576 volt here. What is the next question? Next question is referring to question number 9. If the secondary of the full bridge converter is modified. So now if you see, this is no longer a center tap transformer. This is a two winding transformer and this diode bridge rectifier. So in that case, what will be the peak inverse voltage of the diode? So earlier we had a center tap configuration like this, but now we have a diode bridge. And here we have one single winding instead of two windings. So now what will be the peak inverse voltage for any of these diodes? So you can understand now. Now suppose the diodes will conduct like either these two diodes or these two diodes. So suppose these two diodes are conducting. So then this diode and this diode, they will have to withstand a voltage which is Vs, not 2 Vs, right? Here they will have to withstand a voltage equal to this secondary voltage. So now the PIV is 288 volt. Here it was 576 volt. So for center tap configuration, the diode PIV rating will have to be twice compared to this case. Here the diode PIV rating is equal to V secondary, but for center tap it is twice V secondary. Okay. So I have discussed all the numericals. If you have any question, you can ask. If you have any question, you can ask me. Otherwise, we can conclude today's session.
ये आज अपलोड कर देंगे मैडम आज ये?
Yeah, I shall upload it. But I think today some disturbance was occurring while like sometimes I think due to network issue, I was getting disconnected, or probably in between the screen was also not visible. So I will see. I will upload this.
Okay, thank you.
Okay. Okay, I shall upload then. If you don't have any question, then let's conclude today's session. I shall stop recording.